Imagine a time before time existed, a moment so primordial that even the concept of time had yet to be born. A time before stars ignited, before galaxies swirled, before the first light pierced the darkness, before even the very fabric of space and time themselves had woven the intricate tapestry of the cosmos. Picture an empty canvas, dark and vast, stretching infinitely in all directions, a blank slate, waiting for the brushstrokes of creation. This is the stage upon which the grand cosmic drama of the Ekpyrotic Universe unfolds. A theory that suggests a universe born not from a singular explosive event, but from the collision of two parallel branes in a higher dimensional space. The Ekpyrotic Universe Theory offers a captivating alternative to the prevailing Big Bang model. It proposes a cyclical universe where each cycle of creation and destruction spans trillions of years. It dares to challenge our understanding of the universe's origins and paints a picture as breathtaking as it is radical. Imagine a universe that is eternally reborn, each cycle giving rise to new possibilities and new forms of existence. But before we delve into this new cosmic narrative, let's first examine the familiar story, the Big Bang, and the mysteries it leaves unsolved. The Big Bang Theory has long reigned as the leading explanation for the birth of our universe. The Big Bang Theory has long reigned as the leading explanation for the birth of our universe. It describes a universe erupting from a single point of unimaginable density and heat, expanding and evolving over eons into the cosmos we observe today. It describes a universe erupting from a single point of unimaginable density and heat, expanding and evolving over eons into the cosmos we observe today. This model has provided us with profound insights into the nature of our universe, from the formation of galaxies to the cosmic microwave background radiation. Yet despite its successes, the Big Bang model leaves us with more questions than answers, prompting some physicists to seek a more complete explanation. Questions about what came before the Big Bang, the nature of dark matter and dark energy, and the ultimate fate of the universe remain unanswered. This quest for understanding drives the exploration of alternative theories like the Ekpyrotic Universe that might one day provide a more comprehensive picture of our cosmic origins. Enter the Ekpyrotic Universe Theory, a bold new contender on the cosmic stage. Proposed in the early 2000s, this theory suggests that our universe was not born from a blinding flash of energy, but from a slow, graceful collision of two three-dimensional universes, or branes, existing within a higher dimensional space. Imagine two colossal sheets, representing these branes, floating in a space beyond our comprehension. They drift slowly towards each other, drawn together by an invisible force. The space between them, representing our own universe, is not empty but filled with a sea of energy, a potential waiting to be unleashed. As these branes draw closer, the energy between them intensifies. Finally they collide, not with a deafening bang but a slow, powerful embrace. This collision, the theory proposes, is what sparked the birth of our universe, not a singularity of infinite density and temperature. The Big Bang Theory, while successful in explaining many observed phenomena, faces its share of challenges. Despite its widespread acceptance and the wealth of evidence supporting it, there are still several profound questions that remain unanswered. These questions not only challenge our understanding of the universe's origins, but also push the boundaries of modern physics and cosmology. One such challenge is the singularity problem. The concept of a singularity is not just a theoretical curiosity, it represents a point where our current understanding of physics breaks down completely. In the context of the Big Bang, this singularity is thought to be an infinitely dense and hot point from which the universe began. However, the very idea of infinite density and temperature is problematic and suggests that our current theories, including general relativity, are incomplete. The Big Bang posits that the universe began from an infinitely dense and hot point, a singularity where the laws of physics as we know them break down. This raises the question, what happened before the Big Bang? And can we ever know? Some theories suggest that our universe could be part of a larger multiverse where Big Bangs are common events, but these ideas remain speculative. This concept of a singularity, while mathematically convenient, leaves many physicists uneasy. It implies a boundary to our understanding and suggests that new physics, perhaps a quantum theory of gravity, is needed to fully comprehend the universe's birth. The quest to resolve the singularity problem is ongoing, with researchers exploring various avenues from string theory to loop quantum gravity. Another puzzle is the flatness problem. The universe appears to be remarkably flat, meaning its geometry is very close to Euclidean geometry. This observation is perplexing because, according to the Big Bang model, the universe could have taken on any shape. The fact that it is so finely tuned to flatness suggests that there might be an underlying principle or mechanism that we have yet to discover. Observations suggest that our universe is remarkably flat on a large scale, meaning its geometry is very close to Euclidean geometry. This flatness is not just a trivial detail, it has profound implications for the fate of the universe. A flat universe will expand forever, but the reasons behind this precise balance remain elusive. The Big Bang model offers no compelling reason why the universe should be so finely tuned to flatness. This has led to the development of the inflationary theory, which proposes a rapid expansion of the universe just after the Big Bang, smoothing out any initial curvature. While inflation is a promising idea, it is still a hypothesis and requires further evidence and understanding. Finally, there's the horizon problem. This problem arises from the observation that the universe, even at its furthest observable points, appears remarkably uniform in temperature and composition. This uniformity is surprising because, according to the Big Bang model, these distant regions should not have had enough time to interact and reach a state of equilibrium. The universe, even at its furthest observable points, appears remarkably uniform in temperature and composition. This uniformity is seen in the cosmic microwave background radiation, which is the afterglow of the Big Bang. The temperature variations in this radiation are incredibly small, indicating a high degree of uniformity. However, these distant regions, according to the Big Bang model, would have been causally disconnected, meaning they wouldn't have had enough time to reach a state of equilibrium. This raises the question of how such uniformity could have arisen. The inflationary theory also attempts to address this by suggesting that the rapid expansion of the universe allowed these regions to come into contact before being pushed apart. This uniformity, without a mechanism for these regions to communicate and reach equilibrium, remains a significant puzzle. The horizon problem, like the flatness problem and the singularity problem, highlights the limitations of our current understanding and the need for new theories and observations to unravel the mysteries of the universe's origins. Section 4. The Dance of the Branes, a Collision of Worlds, the Ekpyrotic Universe. Theory offers elegant solutions to these Big Bang puzzles. This theory, which derives its name from the ancient Greek word ekpyrosis, meaning conflagration or out of fire, suggests a radical departure from the traditional Big Bang model. Instead of a universe emerging from a singular point of infinite density and temperature, the Ekpyrotic model envisions a grand cosmic ballet where our universe is born from the collision of vast multidimensional membranes or branes. Instead of a singularity, it proposes a collision of branes, a process governed by the known laws of physics. These branes, which can be thought of as immense, flexible sheets existing in higher dimensional space, move and interact in ways that are still being explored by physicists. When these branes collide, the energy released is immense, leading to the creation of a new universe. This process is not only more intuitive but also aligns with our understanding of physical laws, avoiding the paradoxes and infinities associated with a singularity. This collision provides a starting point for the universe that avoids the singularity problem altogether. The singularity, a point where the laws of physics break down, has long been a thorn in the side of cosmologists. By replacing it with a brane collision, the Ekpyrotic model offers a more palatable and scientifically consistent origin story for our universe. The theory also addresses the flatness problem. In cosmology, the flatness problem refers to the question of why the universe appears to be so geometrically flat, with space-time having very little curvature. The Ekpyrotic model suggests that the collision of branes naturally leads to a universe that is flat or very nearly flat on a large scale. The collision of branes, according to the model, naturally leads to a universe that is flat or very nearly flat on a large scale, neatly aligning with observations. This is because the energy and dynamics involved in the collision would have smoothed out any initial irregularities or curvatures, resulting in the flat universe we observe today. The tremendous energy released during the collision would have smoothed out any initial curvature, resulting in the flat universe we observe today. This smoothing effect is akin to how a potter smooths out the surface of clay on a spinning wheel, creating a uniform and flat surface. Furthermore, the Ekpyrotic model offers a resolution to the horizon problem. The horizon problem deals with the question of why the universe appears so uniform in temperature and composition, despite regions being too far apart to have exchanged information or energy at the speed of light. Before the collision, the branes, representing different parts of the early universe, existed in close proximity within a higher dimensional space. This close proximity allowed them to interact and reach a state of equilibrium, sharing energy and information across their surfaces. This proximity allowed them to reach a uniform temperature and composition well before the collision that birthed our universe, explaining the observed uniformity without requiring faster-than-light communication. Thus, the Ekpyrotic Universe Theory not only provides a compelling alternative to the Big Bang, but also elegantly addresses some of the most perplexing issues in modern cosmology. Section 5, Cycles of Creation, the Universe Reborn.